Hello and welcome to chapter 19, where we're going to talk about some things that are very, very different from what we've been talking about all semester long. Chapter 19 is going to talk about something titled thermodynamics. Hopefully, that's something that you've heard about, whether that was back in high school in chemistry or is a physics class. Thermodynamics is something that's covered both in chemistry and physics. They're very similar, talking about the same kind of thing, but we're looking at it from different perspectives. Right? So, from a chemistry standpoint, thermodynamics is really designed to tell us, does a reaction happen or not? It allows us to figure out, if it's going to happen or not, and what we need to do to make it happen, if we can help that and control that. So again, it goes back to our control of equilibrium. So we're going to be talking about some very different things in this chapter, but we're also going to relate it back to things that we've talked about, whether it goes to solutions, back to equilibrium, back to rate laws. All those things are going to tie into thermodynamics. The one thing we will not be doing in this chapter are ice tables. Okay, I said at the end of chapter 18 we were going to be done with ice tables, and I meant that. So that is the one thing we will not be doing in chapter 19. So let's start with this. So take 15 seconds and just quickly rub your hands together. All right, rub them together really fast. All right, so what happened? What did you feel? Are your hands warm? Yeah, absolutely they are. All right, that is thermal energy, right? And that's heat that we're feeling. It's not temperature, but it's heat. There's an important distinction there. So that's caused by the motion of our hands and the friction of our hands rubbing together makes heat, and that is our thermal energy. So thermodynamics is the study of heat, of the work and heat flow from one place to another. Right? This is talking about the movement of thermal energy and movement of heat from our system, right? The reaction or the process that we're interested in to the surrounding molecules, or vice versa, from the surrounding molecules to the system. And that means it's going to cross over through a boundary, whether that's a beaker or some other boundary. It could be physical or even just the space, a vacuum or space too. A boundary could be just about anything. Right. So thermodynamics plays a large role in chemistry, in physics, in engineering. So you're gonna see thermodynamics in a lot of different areas. So let's first off get this distinction between thermal energy versus temperature down, because this is a very common misconception that people think that these are the exact same thing, and they're not. Thermal energy is the kinetic energy in transit from one object to another due to differences in temperature, and it's joules. It's an amount of energy. Where kinetic energy is a measure of the average kinetic energy in an object. Right? So an object can have a temperature, but when I put two objects together like I have here, there's a flow of heat because these objects are at different temperatures. Right? So the heat flows from the warm object to the cool object until they have the same temperature. Right? So we have our thermal energy in joules, which is what we're really interested in a lot of cases, and then our temperature is simply the average kinetic energy of an object. So we have three laws of thermodynamics. And let's talk about the first law, the most common law, one that we mentioned back in Chem 111. The first law of thermodynamics, which is pretty straightforward and simple. It says that the total energy of the universe is constant. Energy is neither created nor destroyed. However much energy I start with, I have to end with the exact same amount of energy. Right? However, the location of that energy or the form of that energy does change and can change. Right? So where we're moving the energy from is what we're really interested in. So you can think of a lot of thermodynamics, and especially the first law, is kind of energy accounting. Right? We got to keep the books on where this energy is. We know however much we start with, we have to have the same amount when we finish, but where it is and what form it's in, we need to keep track of that. Right? And that's what we're going to spend a lot of time working with. So another example of our first law of thermodynamics. If you picture using a bicycle pump handle, you lift this handle up and down, and that pushes air through the hose into the ball or the bicycle tire or whatever that you're filling. As you do this, you're applying mechanical energy. You're physically lifting and pushing the handle up and down, and that's converting that mechanical energy into some thermal energy through friction of the piston moving up and down and to the friction of the air molecules traveling through the hose. So both of those things get warm over time. If you look at the temperature when you start, before you start pumping air, versus when you finish, both the piston in itself, the pump will get warmer, as well as the hose and the air that you're moving will get warmer because of friction. This mechanical energy is being converted into thermal energy. Another concept that we need to talk about in this chapter is the idea of what a spontaneous process is. So a spontaneous process is one that happens without any kind of outside intervention. That I just put the reactants together or set up the system, start it, hit press go, start it somehow, however is necessary, and then it just happens all by itself. In this example, I have two containers, A and B. Container B has 1 atmosphere of worth of gas in it. Container A has no gas, it's evacuated, there's zero pressure. So unsurprisingly, we know this when I open up the valve, the gas particles will spontaneously travel from container B into container A until they both have the same pressure. Right? That's a spontaneous process. What is not spontaneous is once I have equal pressures in both A and B, to go back to our initial scenario where I had all my molecules in container B and none in container A. That is not spontaneous. That's not going to happen on its own. Right? I would have to do something to force that to occur. And that means that processes and reactions are spontaneous in one direction, but non-spontaneous in the reverse direction. So if we think of our equilibrium, reactions are one of those directions, either products to reactants or reactants products is spontaneous. Right? So in this example, taking an iron nail, it will spontaneously rust if I leave it outside. However, that rusty nail will never go back to being a pure iron nail. That process, the reverse, going from rusty nail, iron oxide to pure iron, is non-spontaneous. Right? And that's really important to know these definitions, these terms for a spontaneous process. And another thing that can affect a process spontaneity is temperature. Right? So some reactions or processes can be spontaneous in one temperature and non-spontaneous at another. And a great example, really simple, is water and ice. So at above 0 degrees Celsius, it is spontaneous for ice to melt. But below 0 degrees, the ice isn't going to melt. That's non-spontaneous. But what is spontaneous is water freezing into ice. And so those processes are absolutely temperature dependent. The last term that we need to introduce right now is entropy. And I talked a little bit about this when we talked about solutions. And we're going to get into a lot more detail, and we're going to start calculating, applying numbers to entropy. So Clausius was convinced that there's a significance between the ratio between heat delivered and temperature. And remember, we talked about that those are two very different things. Heat delivered is the amount of energy that's being transferred, the joules, that's moving from one object to another, where temperature is the average kinetic energy of those objects. So he was able to say that entropy value is equal to this ratio, Q over T. And what this really means on a broad scale is this is looking at the randomness of a system. As entropy goes up, the randomness of the system goes up. Right? So, and this is related to the various modes of motion that molecules can possess. And there's a lot. It's not just straight line kinetic motion of molecules. There's a lot of other various modes of motion that molecules can undergo. And depending on what those modes are, what are available to the molecules, and how vigorous those modes of motion are, is going to determine whether we have a large entropy value or a small entropy value. And we'll get into those various modes in a later section. So like energy, total energy of a system, and like enthalpy of a system, entropy is what we call a state function. And what that means is we can find and calculate a delta value for entropy, just like we do for entropy. So we have a delta S, and that's really what we're concerned with in most cases, is how entropy is changing. So the entropy value of the final state of a process or reaction minus the entropy value of the initial state, and that tells us our entropy change, and that's what's a really useful value and a useful number to tell us what's happened. Do we have a spontaneous process or not, depending on the sign of that delta S value. Is it a positive value or is it a negative value? So we're going to leave it there for part one. That introduces our first law of thermodynamics and a lot of the basic terminology that we're going to need with our thermodynamics discussion here in chapter 19. And we'll pick this up with our further laws of thermodynamics and some of the calculations that we're going to need to do and determining whether or not a process is spontaneous. That's our ultimate goal for the vast majority of work that we're going to do in this chapter, is to determine, is a reaction or process spontaneous or not, and how do I control that? How do I make it spontaneous or non-spontaneous depending on our needs? All right. Thank you very much, everybody.